Click. Boom. Okay. It's all yours. What questions do you have for me?
For 15.74, I just want to know, do you ever make? So if the R is negative, would that change the angle? You know what I'm saying?
You can, if the R is given as negative, then you can,
If we had to change from that angle to an angle,
right.
so
Well, let's think of it this way. We had the point -2, 2, and then a z value, right? So let's just think of x and y for the moment. If I want this to r theta, it's there, right? Are they both negative or is just one negative? Oh, see, yeah. If this one is positive, so it's not here. It's here, right? So you have two choices. You could use this theta and a positive r, right? Or you could use this theta and a negative r.
yeah.
So it's really your choice on whether you do r being positive or r being negative. By default, I tend to think in positive r values, but I can do it either way. I realize now that I'm looking, those are not the right numbers, but that's the right idea. Yeah, you can use r positive or r negative, depending on which you find more appropriate to the situation. Again, I'm going to go with force of habit. Most often I think of positive r, especially when I think of bounding regions like inner and outer, I think of positive values of r. More questions?
Same for spherical. Or you could do it.
Yeah, but in spherical, you're going to have to watch both angles, right? Because if I'm saying go this way and that way, but go negative, that's the same as saying go this way. So both both theta and phi will change if I move from a positive r to a negative r. Face this direction and back up. Twitch, twitch, twitch. I don't like driving in reverse, much less flying my spaceship. Although I did read that scene. There's an idea in interstellar travel called a Bussard ramjet. And instead of using fuel you bring with you, the Bussard ramjet uses interstellar hydrogen to drive a fusion. But what you get is you get a very, very large funnel made out of a magnetic field. You take a very thin piece of wire and put a positive charge on it, spin it, you get a magnetic field. This is physics too. I remember this. So you have this spinning vortex that gathers in hydrogen. And as long as you're accelerating, you have gravity on the ship. So instead of coasting, because you're just sucking in hydrogen for fuel wherever you are, when you get to the middle of your flight, you turn the engine off and pivot the ship. And you fly the last half of your thing backwards. In reverse, gathering and pointing the engine this way, slow yourself back down. So your braking maneuver and basically turns yourself around and flies backwards for half your flight. It's how the original lunar landers land, right? They point themselves to the ground, they start falling. And then they hit the engines to brake and land safe. So in spite of me not liking negative R values, we use them a lot. More questions?
So the interval for 15,720.
15,720. The solid that lies between the cylinders x squared plus y squared equals 1. Well, it says between the cylinders x squared, x squared plus y squared equals 1 and x squared plus y squared equals 16.
My book said -1. In the normal version,
That's a typo.
but that makes sense. So, no.
Okay, I can stop you then. Sure. It says between these two cylinders, above the XY plane and below Z equals Y plus 4. Now, my first thought is to figure out what this looks like. But that's just in Y and Z. So in spite of me having an X in this direction, I don't really need it at the moment. Z equals Y plus 4. Is a plane, because in just Y and Z, it's a straight line, which means really it should be a surface this way, right? Okay. So there's my plane. And now I've got those are circles, right? X squared plus Y squared equals 1 and X squared plus Y squared equals 16. Great. Circles. They're circles in the XY plane, but since there's no Z, they're cylinders. They go up and down. So I have a circle down here of radius 1. And I have a circle here of radius, which means it's going to touch right here, isn't it? Wait a minute. That means that our plane comes down and touches the very edge of that circle. Good. Because that means the bottom can be the XY plane and the top can be that oblique plane. So I have a floor and a ceiling. And then I have a region in the XY plane. So this is dz dA. But I'm doing dA in polar, so this is dz dr d theta, rdr d theta. Fabulous. If I'm going to do it, dz r dr d theta, I need to know two things. One, what am I integrating?
The x minus y, well, we gotta turn it into.
What's the actual question asked me to find?
When it's solid.
It asked me to find something about the solid.
We need solid that y and stuff.
Evaluate. What am I evaluating?
Yeah, x minus y.
Okay, so x minus y. F of xy equals x minus y. And you're right, I need to turn that into polar. Okay, and then I need to put in all the boundaries. So, x is minus y is dz r dr d theta. I didn't leave enough room, so I'll rewrite that. And then I need the limits. Z limits. Z limits come first. Now, here's where I could be sneaky about it. The Z limits are here. What's the lower limit in Z? Bingo, because it's the XY plane at a height of 0. Now, since we've already turned all of this into r and theta, I should turn that into r and theta as well. R sine theta plus 4. Right? And then, what are my r limits? And my theta limits. Because I'm going all the way around. Here's the sneaky idea. I could have said, this. I haven't changed it to r and theta yet, have I? But then I can do that integral in x and y and change after. It's your call. You can do it either way. When do you make the switch to polar? At the beginning? After you've done the z part? It's up to you. It said use cylindrical, so my brain went right to doing everything in r and z and theta. Fine. I'll do it here. But this and then converting to r and theta will give me the same result. As long as A down here is the annulus, that's the region between two circles. It's a flat donut. You could call it R, you could call it D, I don't care. More questions?
Eight.
15, 9, 8. Find the image of the set. S is the square in U and V bounded by 0 and 1. And our transformation x equals V, y equals U times 1 plus V squared. With me so far? Pick a side. Over there in the square, we're going to do the same four idea setup that we did in class. So pick a side. Which side do you want to do? So the bottom side, side 1. What do I know about side 1? I know that all the V values are 0 there. And I know that U goes from 0 to 1. So then I go over here and I say, oh, well, then X is going to be 0 all the time. And Y is just going to be U times 1. Wait a minute. U is trapped between 0 and 1. It means Y is trapped between 0 and 1. And X is always 0. T of side 1 goes from here to here. And I can even think of it as being oriented, right? If I think of U starting at 0 and going to 1, then I can think of starting at 0 and going to 1. 3 more to go. Now, I'm sure that when we're over here on side 2, the fact that U is always equal to 1 but V is bounded between 0 and 1, right? Well, that means that X goes from 0 to 1. And Y is 1 times 1 plus V squared. But wait a minute, V is equal to X. Y equals 1 plus. That's a parabola. When X is 0, we're at this spot right here. When X is 1, we're at Y equals 2. There's T of side 2. On and on we go. Finish out what this shape is. Make sense?
Can you just do side 3?
Sure. Well, okay, side 3, I'm assuming is the top. Okay, no. If that's side 3, that means that V equals 1. And if V equals 1, and U is trapped between 0 and 1, right? Then I get X equals 1, and I get Y equals U times 1 plus V squared. What happens when U is equal to 1?
2.
And when U is equal to 0? So as we go, now notice the way I'm going here. I went up this side, right? Now I'm going that way. So I start here where U is 1, and I go down to where U is 0. No, but I'm just trying to show you how I'm walking around the, gee, I wonder where side 4 is going to go. I promise thinking about the arrows is actually going to be helpful a week and a half from now.
Basically, the numbers to the,
Well, as soon as I know what the curves look like, I know where they start and end, right? This is y equals 2u. That's a parametrically defined straight line. Because x is always equal to 1. Now I just need to know where to start with it today. The reason I'm drawing the arrows at the moment is because when I think of something like the unit circle, I think of going around the unit circle counterclockwise, right? So I think of there being an orientation. We did this with our parametric curves, right? We drew the little arrows on our parametric curves. These are parametric equations up here. So I'm kind of thinking about what happens as my parameter changes. How do I move around that square? How do I move around this piece? Notice something interesting over there. I'm going around that counterclockwise. What about over here? Ooh. Somehow there's a flip involved here. Counterclockwise over there and clockwise over here. I wonder what that does to my integrals. You ready for me to be really sneaky? No. Promise it's small. Let's do the Jacobian of this one. There's my transformation. The Jacobian is derivative of x with respect to u is 0. Derivative of x with respect to v is 1. The derivative of y with respect to u is 1 plus v squared. The derivative of y with respect to v is 2vu. When I do that, I get negative 1 plus v squared. My change in area is negative because I flipped over. And that's why when we actually do the Jacobian, we take the absolute value. Because I don't care when I'm doing the integral, I don't care what orientation it is, I care about the distortion. That's why we take the absolute values in our Jacobians, in the integrals. But here I can actually see what that negative sign means is that I turned the region over somehow. In a three-dimensional Jacobian, that would turn one of my vectors the wrong way. And I'd have a left-handed change, right? My little volume would turn itself inside out. The very first Star Trek movie. I'm old. The very first Star Trek movie starts with a transporter accident. If you watch the reboot where Leonard McCoy refuses to get in the transporter, he gets on a shuttle instead because he knows of this transporter accident. What happened with this transporter accident? I swear to you, the script says there's a Jacobian reversal. And the people had turned inside out. The writers were not stupid. This is the same reason that when you switch two rows in a determinant, you get a negative. You reverse two coordinate vectors. And that's why all of your data calculations are then squared and square rooted. Ignore all those reversal of order effects. More questions? Go ahead. Ain't nobody else volunteering?
For 15,916, tell me, can you tell me get the limits for the integration? Like how you got, you like, do you know what I'm trying to say?
Yes. So, yes. So remember that the parallelogram in question has as its vertices -1, 3. 1, -3. 1, 5. And 3, -1. Right? So let's draw those, because I'm pretty sure that something really nice happens here. -1, 1, 2, 3. There's this point. Oh crap, I'm gonna go off too high. Let me redraw that over here. 1, 2, 3, 4, 5. I need to go up there to 1, 5. -1, 3. 1, -3. And 3, -1. Right? Now, what are our transformation equations? X equals and Y equals. This is the region R, which means this is in X and Y, right? Let me start with that side. That's a straight line. It's the equation for that line. Right, because it's got a slope of 1, and it's got a y-intercept of 4. You ready for my sneakiest maneuver of the day? X equals Y equals. Put them in there. I want you to simplify that equation. I'm going to start by multiplying by 4. V minus 3u equals u plus v plus 16 now, right? Wait a minute. There's a v on both sides. What happens? If I move that over, I get -4u equals 16. U equals -4. Oh, there's a boundary for the region back over here in the UV plane. If you can figure out the other 3 sides, you can figure out the other 3 boundaries over here. What you just asked me to do is this backwards.
So,
Okay.
yeah, so I did like, so using the equation on the left, and then point to be -1 equals 1/4, even b whatever, and then 3 equals 1/4. B, C, and then I set those equal to each other.
Yeah, you're solving the simultaneous equations here, right?
Just got, I got like 8 different values, but they were all like, it was like, well, not different, but your way makes more sense.
So, but here, I've multiplied by 4, right? And now I'm going to do elimination by addition. So I make this a negative, and I get 4u equals minus 16, u equals -4. Now you can go back and get a v value, right? That tells you one corner of the picture over there. As a matter of fact, if you look, you're going to get the same numbers. You're going to get the 4 different values 2 times, right? You'll get this u equals -4 somewhere else. That's a vertical edge, u equals -4. And then you get a v value. And the corner you come up with, I think v is 0 here, right? So that's one corner of the region you're describing in the UV plane. Now, because this is a very, 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 very big problem, I'm going to get a rectangle over here. Which is why I only need to know where the corners are. But as we saw, sometimes we don't get vertical lines and horizontal lines. Sometimes we get angled lines. There was that one in the book, looked like a trapezoid that was upside down. So I prefer doing it by the line rather than just by the corners. Because I think that tells me where this whole thing goes. But this doesn't not work. It's just because this problem is rigged, it works so nicely. If I were really being very pedantic about it, I could take those equations for x and y and solve for u and v, right? And then I have the transform that went this way instead of this way. I'd have the inverse transformation. Then I could do the Jacobian of that. And do a nice property of determinants that will be 1 over the Jacobian I want, when my transformation is linear. And this one is linear because it's all straight lines. You sneaky booger. I hit a linear algebra problem in the Calc 3 class. You had a question as well, Jack.
Yeah, so originally it was actually about that one, but you answered it, and then I also have a second one, for 24, of the same section. I was just wondering about the, really, I'm like the appropriate change, like I'm just, like, kind of freaked out on the appropriate change part.
Right, because there isn't the transformation isn't given to me, right?
Yeah.
So the real question is, what would be a good transformation here, right? And what are we told about the region?
It's a rectangle.
But it's bounded by diagonal lines, isn't it?
Yeah.
X minus y equals 0. X minus y equals 2. X plus y equals 3. and x plus y equals 0. Hey, wait a minute. Those are all just numbers if I were to use these. Wait a minute. What if I let u equal x minus y and v equal x plus y? Now, let me go over and look. That makes sense here. Does it make sense here? Well, there's a v. What about that piece? That's the difference of two squares, isn't it? X squared minus y squared is equal to
X, not X, but sorry, X plus Y, X minus Y.
which would make this v e to the v u. Son of a. This is the transformation I'm going to use right there, because that's where my pieces fall out really nicely, aren't they? Hot damn. This is actually the hardest part of transformation ideas, is figuring out what the change of variables should be. And when we have a region that isn't predefined nicely, then figuring out what that transformation is sucks. But if I happen to say, oh, look, these are all bounded by straight lines, and those straight line pieces happen to show up here, then my all of a sudden just fell into my lap. Again, as I said earlier to Mia, as these problems are really, 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 really rigged, this shouldn't be as insane as it could be. One thing we find out in the long run is that when we come to doing actual real world problems, finding the region to integrate over properly is one of the hardest parts. There's an interesting picture in the previous section, in 15.8, where they talk about spherical coordinates. They give this picture on page 1051. What the hell is that? Oh, it's a radial thing bounded by two different sine curves. So it wiggles back and forth as we go from top to bottom, and it wiggles as we go around. So they're literally calling it a bumpy sphere. Why the hell would you use this? Well, according to them, it's a good tumor model. I'll go you a step better. There are similar versions of this that are cellular surface models for the membranes of cells. When you have different chemical concentrations on the outside and inside of the cell, the diffusion causes the cell membrane to change. You get something that looks very similar to this. If you're doing molecular chemistry, that, as opposed to biochemistry, that's an important idea for an electron orbital. That same sort of weird behavior looks like an f orbital or a d orbital, and all of a sudden the quantum chemistry students are going, I've seen that too. Finding the right region to do the integrals on sucks. But now that I have this, I might be able to do some sort of nice transformation to get rid of some of the trig functions to make the region I'm integrating on easier. Because I'm going to end up integrating this thing. And that's disgusting. But if I switch to spherical coordinates, which gets rid of all the trig functions I want, this becomes rho. This is e to the minus rho squared sine phi d rho d theta dv. This is an easy integral to turn out. But I wouldn't have known that looking at this to start with. Now, one of the more interesting recent uses for that bumpy sphere idea is chemotherapy. Targeted chemotherapy. Chemotherapy is atrocious. Here, I'm going to poison you, and the cancer will die faster, and then we'll cure you, and the cancer will be dead. Have you lost your fucking mind? But that's really the way chemotherapy works. Radiation therapy says, I'm going to irradiate this little piece of bad thing inside you so it dies, and hopefully the radiation poisoning that I'm giving you doesn't kill you along with it. You'll pardon my bluntness. This is bullshit. So, targeted chemotherapy takes objects that look like that have characteristic diffusion of the chemical from the inside to the outside, and inject them directly into the tumor. So that the only place the chemical goes is the tumor. And because it's a time delay of how fast the chemical comes out of the surface because of the bumpy surface properties, you only deliver the chemical right there. And that means the rest of your body isn't poisoned along with the other stuff. My father, when he went through his leukemia treatments this past year, fortunately, he had a very, very, very minor CLL, a very light version of leukemia, crazy sentence to say. He had a mild cancer. Well, they gave him immunotherapy instead of generalized chemotherapy, and it treated his body very differently. But the man broke out, had a skin rash for probably 3 months. Flaking, peeling, looked like he'd been sandblasted. Why? Because he had to take this thing to his whole body, not just out the spots. That fixes it, but only because I could figure out how stuff moves across that membrane. Guess what we're doing in next chapter? Intramembrane transports, going across surfaces. That's where this leads. Useless, never going to use it anywhere. I'm going to prevent people from dying by doing this stuff. If I can do it right. And I can ameliorate hair loss, right? Because one of the side effects of most radiative therapy and chemotherapy is hair loss, right? Radiation poisoning, I'm chemically poisoning you, your hair gives up and leaves. I don't have to deal with that if I can target these things better. All right, I brought us down enough. Ask me more calculus questions. Exam review. I've got office hours this afternoon. Got office hours tomorrow afternoon, right after class. If you've got questions, you should come bug me. At the beginning of class, when I collect everybody's homework, I'll post all the keys. And we will have them from then forward. Tomorrow I have a meeting at the end of the day. I got another event in Pittsburgh, so I promise I'll grade your homework tomorrow. But I'll post the keys early just in case. See you all tomorrow then. A wonderful rest of your day.